Okay, so the second part today is about bitmap indexes. And I mentioned that already. We had this top 4 list of index structures. And that's kind of on the fourth place in a way. Yeah? So B trees and hash tables being the most important. And we have periodics, trees, and tries getting more important in the context of main memory database systems. We will look at that this Friday. We look at radix, tries, / trees this Friday. But today we look at bitmaps. And why bitmaps? They're easy and flexible. They can encode arbitrary predicates. They're very useful for heavy queries, meaning you have many filters, many joint predicates, and large data sets. So, I mean, it really got popular in the 90s for so-called data warehouses, so for online analytical processing. And those were queries on large schemas, many joints, many large data sets. And you simply couldn't handle these queries with existing indexes anymore. They were too heavy for that. And there were a couple of interesting proposals to use bitmap indexes, and they really sped up query processing for that. So the primary use cases for bitmap indexes are read-only or read-mostly scenarios. Why is that? Because bitmap indexes are very hard to update. It's very costly to update bitmap indexes, as you will see. Maybe a clarification about this read-only and read-mostly scenario. I try to spell it out here. Why isn't this going away? So try to spell it out here. So read-only means there's only read operations in your database system, but no inserts, updates whatsoever. Yeah. An example for that are search engines or online analytical processing or all kinds of analytics. Of course, I mean, at some point you want to update your index, you want to update your database, but in a read-only scenario, this doesn't happen through single updates typically, but through batches. So you have many, many updates you're collecting, and then you apply them somehow to the index. Basically, you merge your changes into the database and then recreate the indexes typically. Yeah, still, these scenarios are called read-only. Of course, that is a lie. It's not purely read-only, because once in a while you have a batch of updates you apply to your database system, but still we talk about read-only. The same or similar lie is when people say it's write-only. So there's no read operations, only updates, inserts, and deletes, which doesn't make too much sense, yeah? Because that's the equivalent of def null on Linux, actually. You're only writing, but you're never reading from def null. I mean, what's the point of writing stuff somewhere and no one reads it, yeah? So, of course, most of the time it's writing, but like archival is a good example, yeah? Okay, oh, now it's better. Okay, so could you hear what I said in the first part? It was very loud, right? Okay, so thanks for that. So now the microphone's up again. Yeah, write only means no read operations, only updates, inserts, and deletes, and archival storage is a good example. So archival, of course, that's also a lie. I mean, you archive, you do backups and stuff like that, and for most of the stuff, you never look back at that again anymore. But once in a while, and 100 years from now, someone looks at it, so he or she is reading. So it's not purely write-only. Yeah? It's more like write-only is more like 99.9% writes, and read-only is 99.9% reads. But the naming is like that. Yeah, and then there are these scenarios in the middle, wherever you want to put them. So read mostly means most of the stuff is reads. Few updates, inserts, and deletes. A good example for that is IMDb, actually. Yeah, so it really depends on your database system. It's not too many movies that are produced in the world, yeah? But for each movie, you create a couple of tuples, you add the relationships to actors, maybe you add some new actors who played for the first time in a movie, stuff like that. So it's a couple of dozen tuples that are added to the database. But contrast that with the people reading from IMDb. Yeah? Whenever you open the website and you read tons of data. So most of the stuff is still reading, but the modifications are relatively little in comparison. Yeah? In contrast, write mostly, this is a scenario that you see, for instance, in monitoring scenarios. Traffic monitoring, for instance. Think about a scenario, doesn't have to be the NSA, just an application monitoring which car is driving where. Yeah? And then you have the GPS information, and that changes like all of the time, theoretically, yeah, and practically only for the cars that are driving. Like cars stand still like 23 hours a day on average, something like that. Yeah, so most of the time it's actually not changing, but for the driving cars at least, you can make the argument, yeah, okay, that changes all of the time, so there's many write operations and maybe only few read operations in contrast. And that's the write mostly scenario. No. Okay, but it depends on, it's in the eye of the beholder. So it's really, yeah, if in doubt, ask back if someone says read mostly or write mostly or any of the other scenarios, what is actually meant by that. But these terms are just used frequently. Yeah, and now we embark into bitmap indexes. And it's actually 2 slides to define many classes of bitmap indexes, and those are the 2 slides. So it's relatively easy. So by bit sequence, I mean an ordered sequence of n bits, and I call that a bit sequence S. Not strike through, I just wanted to underline. A bit sequence S. And the important thing is to understand a predicate encoded bit sequence for K. So we need 4 things for that. So first we need a sequence of objects. So here I'm making a difference to the standard relation definition. We have sets, and really when I say set, I mean this is not ordered. I have no idea what the order is. So we need a sequence. You need a stable sequence, otherwise the things won't make sense here. So a sequence of ordered objects, like in our key value store, in this version key value store we use in this lecture. That's the first thing. Then we need a predicate that should be defined on those objects in R. And then we need a key projecting, do it here. Yeah. I need a key, a projection projecting such an object from the sequence to a specific key. And then I need the domain of those keys. Maybe we start with an example to first show you an example. That's always easier, I think. This is a 10B slide set. So if you look at this relation, you see, okay, we have this relation here with 3 columns. And I will only care about this column here, on the city column. I will create a bitmap index for that. That is the goal here. So what the projection function, so basically my objects, this is a sequence of objects here. My objects are tuples, yeah, in this universe. So each of those is an object, and so forth. And I have a sequence indicated by that arrow. And now I want to create, and I have a projection. The projection is giving me for each of those objects the value of attribute city. That's my projection function. Standard relational algebra projection, nothing different. Yeah? And what I want to have is all the possible outcomes of projecting to city given this specific instance of this table. So given those objects here, what are the possible outcomes? Well, that's only 3. Yeah? The set of values returned by the projection only contains 3 elements: New York, Cupertino, and Berlin. Yeah, you see it here. And if you go back to our definition, then I think that makes a lot of more sense now. That's what I'm doing here. So we have a sequence of objects. That was the table. Then we have this predicate defined on the objects. We are not there yet. We don't need it for the moment. But we have this projection projecting such a tuple to this city column, or the city attribute in this example. And then we have this set of possible outcomes of the projection. So for each and every tuple, I'm feeding into the projection. And that's what I'm doing here. For all these tuples that are contained in this R, I compute the projection and collect that in a set. And in the example I showed, this only has 3 different outcomes. So that's a domain of keys, a domain of projected values that I get from that. Yeah? Kind of makes sense? Yeah, you see it in the example. When we go back here, oops. Yeah, so here my set K, yeah, is all the possible projections I have for all the tuples here, and that's basically these 3 values here. So that's basically New York, then what do I have? Berlin, and Cupertino. Cupertino. That's K. Okay, so far so good. Now, the next step, once I realized I have this set of possible outcomes for this projection, is that I can use it to create an index. And that happens on the next slide. For the moment, some terminology. This is just saying that I have to go into presentation mode. This is the terminology we use here. This means for any K, so for any of those elements in that set capital K, this is called the P-encoded bit sequence of R for key K. Okay. Now what I do is, in the next step is I create an index. The index creates for each element that I find in the capital K. Yeah? So for each small k in K, I create such a sequence that is encoded by a specific predicate. Again, let's switch to an example. Here we go. In this, I'll remove what I just wrote. Oh, okay, let's remove it. It's not so cluttered then. Right. Yeah, so this is my bitmap index. And the bitmap index uses as a predicate equality, and it has 3 bit lists. Yeah, that's a bit sequence. This is one bit sequence, this is a bit sequence, and this is a bit sequence just visualized side by side. And now, if you look at that, what that means is this is set to true if the value, the data value of the city attribute column is equal to what I have on top here. Then it's set to 1. Yeah? Otherwise, it's set to 0. We also see that indicated by the colors here. Yeah, here you see this yellow color, green color, and so forth. Yeah? So here it's all green, everything else is 0. That is my bitmap index. Yeah? This is using equality as a predicate. So does anyone see a problem with such an index, or what do you see as advantages? What could you do with such an index? What kind of operations can I do? What kind of queries or predicates in the query, in a where clause? Yeah? If you have a specific where clause now, you might, yeah, for every where clause in query optimization, you want to find out whether you have an index that will help you in evaluating the where clause. But what kind of where clauses can you do here with that index? Is that, yeah?
City equal New York and have this bitmaps.
Yeah. Yes, exactly. Yeah? So you have a condition in your where clause where, where city equals New York. Yeah? Assuming the database understands my handwriting, you can directly map that to this column. And you know exactly which of those columns have this value set. Yeah? Easy. What if you have other queries that are possible? What kind of queries could you evaluate with a bitmap like that? Yeah, and it's not so easy here. Also because there would be a set-based entry, but or makes a lot of sense. Or city equals whatever Berlin. Berlin. How would you evaluate that? What is the result?
Look where New York or Berlin is one.
Right, yeah, but in processing-wise, you could just OR the bit lists for that, obviously. Yeah? So you take New York, bit list, this bit list, OR them, get a new bit list where the stuff is set. Yeah. So for instance, for what did we say, New York and Berlin? Here's the 1, 0, 1, 1, and so forth. Yeah. And you can directly use this bit list, the computed bit list, to evaluate that stuff and look it up in the actual underlying table. Yeah, that's one thing you could do. What about a query like city equals Saarbrücken? Yeah, maybe someone else? Do you raise your hand?
Access to all the names in the index, and you could just check if the button is.
Right, yeah, that's what happens. There's always a mapping from this data value to the bit sequence. I don't have such mapping for Saarbrücken. This implies this key doesn't exist in the underlying table, which means there's no result. You don't have to do any processing on this table, already done. So very cheap. Yeah? So this is existence query for stuff that doesn't exist. Yeah? Right. Good. So here, okay. Here also, so this was on this one attribute. Yeah? Here I created a bitmap index on attribute city, but we could also do it on street. For instance, here I did it on street. We have 4 different values here. So I have 4 different bit sequences here in this bit list. And now what could you do with that?
Conjunction or disjunction predicate
Yeah.
on both the attributes that you could get and or.
Yes, any and or not, whatever, right? You could do with that. Yeah, for instance, give me all the rows where, whatever, you have Uni Street and whatever, Berlin at the same time. You just compute the bitwise AND operation over that, get the result and use that directly for lookup. Yeah? So these bit operations make a lot of sense because they map perfectly to a machine. Yes, you don't. Yeah. So basically, you can now think about, okay, how do I even represent a bit? Yeah, you represent a bit by a bit. Makes a lot of sense. Yeah. If you have a 64-bit machine, so one of these words gets 64 bits for 64 rows. Yeah. Or this also maps super well to SIMD instructions, so larger words can be processed super efficiently with SIMD. Yeah? So you can do all kinds of fancy SIMD operations very quickly. Also, in terms of memory pressure, this is fantastic. This is close to nothing in terms of memory you're touching in these operations. So this is why this is super fast and makes a lot of sense. Yeah, we talked about that already. It's just placeholders. Right, and and or building blocks for query processing. Yeah, you can, of course, yeah, we can think about, okay, what is the space you're wasting for that? There's overheads for creating those indexes. But can you come up with a scenario where a bitmap index is probably better than wherever it doesn't work so well? What are kind of things to look out for when creating these indexes? Maybe if you go back to our original example here. Yeah, this is the original example, just a couple of rows. It has 12 rows. No matter what you do, no matter what query processing you do here, it will be like this. Please don't create any indexes on this table. Don't create a bitmap indexes for 12 rows. That doesn't pay off, I guarantee. Yeah? Of course, there's an argument, okay, but what if my table grows to 3 petabytes? So I already create the index. Okay, that's a fair software engineering argument. But in terms of query processing, no index in the world will help you with this data. Yeah. Okay, but yeah, do you want to say something?
So it doesn't make too much sense to create a bitmap index for attributes that have a lot of different distinct values.
Yes.
You have a lot of redundancy for all the zeros.
Yes, that is the answer I was expecting. So these nice examples on my slides always have this fantastic property that there's a lot of redundancy here. Yeah, so there's tons of repetitions, yeah, of course, in real data, and depending on the semantics of the column, it might be, I mean, look at a key column, for instance. Key column, primary key, they're all pairwise different. It doesn't make too much sense to create a bitmap index. But the fewer the distinct values, the less space you will need. Yeah? The more distinct values, the more bit lists you need. And then you have all these zeros being there. Yeah? In a scenario like that, it's always like that within every single row, you only have one of the zeros being set, obviously, by definition. Yeah? All the other zeros are set to 0. All the other bits are set to 0. Yeah? If I go back to this example, you see it better. There's always 1 0 being set here. Only 1 0, because there's only, based on equality, there can only be one value. So in the other bit sequences, it must be set to false, to 0. Yeah? Only in one cell it's set to true in one of the bit sequences. Yeah? So you might be wasting a lot of space underneath. And that quickly leads into the discussion that you don't have to represent each and every bit in the implementation. You can compress these bit lists, and you can compress them like crazy. Yeah, we will do that in January and talk about that in more detail. But it's an important trade-off to understand, okay, what are the number of distinct values in my column I want to create an index on? That's a very important thing. Let's jump over that one. Yeah, another thing, and that maybe that brings us into the game. In that definition on the slide, I had this idea of a predicate, and the predicate I showed you so far was equality, but you can use other predicates to encode your bitmap, and that's what I'm doing here. This is a range-encoded bitmap. No, this is still, so for comparison, still the old bitmap. Yeah, so assume a situation like that. You have the year of birth here. Yeah, and you could encode that by collecting all the individual entries here, and then have bit lists here for each of the values. But then what if you have a condition like smaller? Maybe someone is younger or older than a specific year. Yeah, that's not so easy to do here with that one. But you could change the semantics of the predicate to say, okay, is the value smaller equal a given value? That's what I'm doing here. So now the semantic changes. Yeah, it's not equality, but it's whether the predicate is fulfilled. So the predicate is saying, is the value smaller equal than what I have here as my k value? Yeah, so here, only for this row, does that hold? Only for this row, this is smaller equal this value. Then if you move on to the next 1980, yeah, this must also be set, of course. Yeah? This must include everything that was included on the left, of course. Yeah? If it's smaller equal 90, if it's smaller equal 1979, it's by definition smaller than 1980. But it also adds this other bit here for this value. And so forth. For 1981, you keep all the bits from the previous bit sequence, but you keep on adding and so forth and so forth and so forth. Yeah? This is a predicate encoded bitmap, and you can use that to directly look up whether it's smaller, whether it's equal or whether it's greater than a given value. So there is, so yeah, this trick. Yeah, here actually you can drop this last column here in this representation. Why am I dropping it? Of course, all bits are set. It's kind of redundant, yeah. Yeah, of course, to facilitate the implementation, yeah. But now in your bitmap, you would have to have a placeholder to still allow for queries, but just some shortcut saying, yeah, no, everything is true, everything is set there. Yeah? But you don't really have to represent a bit sequence where everything is set to true, of course. Yeah, and then we can go through these operations a bit. So year of birth, smaller equal 1984. How do I do that? How do I answer that? So here, what's the kind of bit operations I need to do to answer these things? Proposals. Yeah, semantics of a single bit sequence is smaller equal. So if now you have an incoming query with smaller equal, how do you answer this query? That's the bit list, yeah? That's directly this bit list. This is the result. Yeah, done, yeah? That's easy. Okay, next one. Strictly smaller 1984. Yeah? Yes, 1983. But not 1984, yeah? Which works here as we are in integer semantics, yeah? But there can't be anything in between 83 and 84. Yeah? You just basically you go one column to the left. There would be one way of doing that. Yeah? What about equality? How do I do that? Yeah? Okay, 1983 is the index, or the bit sequence, and we have the index on 1984. And you said, I want to have everything where there is a difference. Yeah, how do I get that in a bit operation? XOR. XOR. Why XOR? If it's different, it gives you 1, otherwise it gives you 0. We have the special case that it can only be different to the right, because the right column is adding a 1, but that's actually the case we want to have. There's a new bit being set. If both are set, we get 0. So that's not something we look at. And if both are 0, we get 0. That's not something we look at. So that's exactly right. XOR is giving us that information. What about greater 1984? Strictly greater. Yeah. 1984 and 1986, but think again about 1987 is also there, and the 1987 is all true, right? So if I take the index for 1984, which rows, so this means everything where it's set, it's smaller equal. Now I want to have everything strictly greater. Right, and what is the opposite in not? Right, huh? Not, I'll write it like whatever. Not, yeah, something like that. And that gives me, for instance, this one, this one, this one, and this one. Yeah? Finally, boom. Finally, we have this one. Greater equal 1984. So 84 is included. What is that? Yeah, someone else? Just the two, it's okay, but... Yeah, then you again.
Strictly greater than 1983, so we can just say not the bit list of 1983.
Right, not the bit list of 1983. So that's the same as strictly greater than 1983, which means we could just invert this bit list, which is those zeros. Yeah? So with these rewrites, those are also called predicate rewrites or query rewrites in a more general sense, you can still make use of such an encoded bit list. Okay. But the big the big advantage, of course, is that if you have queries coming in like that, you can directly answer. I think for all of these, we could directly answer them by looking at one bit list. In contrast, if you don't have it encoded like that, and you have many of these bit sequences, you have to OR all of these sequences together, and that might be way more work. Yeah? So it's a trade-off. Depends on the types of queries that are coming in. What is the best configuration here? Is it predicate encoded or predicate being equality encoded? Bitmap may make a difference here. Okay, let's look a little bit at the implementation. As usual, we have system. We currently have bit sequence here. Maybe that will go to some sort of util directory eventually. I think this is in interfaces, right? Interfaces, bit sequence. So there's always typically you will see the same file name in the interfaces directory, and then there's a same file name, the implementation in the system directory. It's a bit like header and CPP if it were C++. So here we see how that is defined. So that defines a bit sequence, also called bit vector, bit array, or bit list. So you will see that in literature, many different names. We initially had the name bit set, and again, set is confusing with, you then always have to say, do I mean ordered or not? So that's why we try to avoid the name, but sometimes you see also the name bit set in some of the implementations. We are calling it a bit sequence in this lecture. And basically, you say what are the number of bits, and then in Python, you can overload the operators just like in C++ by overriding these functions. So with that will allow you to do stuff like that. If you have you eventually in the code you create a bit sequence 1 equals ta-la-la-la-la, bit sequence, BS is an unfortunate abbreviation, I have to live with that, BS1, but then you can basically do stuff like that. You can, in particular, use the bitwise operations as if you were handling integer values. That's a great example for operator overloading because you can work with these things directly. I can do stuff like this. And this is enabled by overwriting the operator seek. That's all you're seeing here. Right. Here we also define iterators, returning us the positions that are set in a given bit set. We'll see that later in the algorithms. Then we have implementations of these bit sequences, of course. Again, the question is how do you map a bit sequence to something underneath? And that is what these implementations are doing. Again, you have to specify the number of bits in that bit sequence, and then based on that, you implement you implement that through a specific mapping. Maybe we look at the tests here. It's more insightful. So tests, bit sequences, bit sequence tests. here wasn't necessary to write it there. Yeah, that's again, this is here a test method written against the interface. So with that, I can check different implementations of my bit sequence. And that's what I just showed you. Yeah? Now you can basically write down these things as if you were handling integers, yeah, or these bitwise operations, and then I expect certain values, and I can call this method with different implementations. And that's basically what we're doing here. So we have an integer bit sequence implementation and a bit list bit sequence implementation, and then we create instances of that and expect certain operations. Yeah? So for whatever we create as bit sequences, yeah? So we loop over the different instances, then we can test whether those operations work for this specific implementations. So in practice, you have, again, tons of options to implement such a bit list. So a straightforward way would be to have a list. Yeah? Let's say we have 42 bits. 42 bits we want to represent. What can you do? Yeah, you have a list of Boolean. List of type bool. And that has a size 42, of course. Yeah, in Python, that's a straightforward way to do. That's one way of doing it, probably not that efficient. What you could also do, and then it also quickly embarks into what is my programming language doing underneath on C++. There's this problem typically that if you, that bits are mapped to bytes, at least it used to be like that. So even though you assume that you have a bitwise representation, then you create an extra byte and then run into trouble. Of course, what you do is typically you map it to words. Yeah? So if you have a word of 64 bits, yeah, what you need is a list of whatever int 64. Yeah? If it were C++ or something like that, in Python that's not the case because the integers are unbounded. Yeah? But then you would basically divide by your word size. Yeah? So if you have n bits to represent, you divide by 64, and that gives you the number of words you need in your list. Yeah? And with that, then you basically rewire all the bit set operations. Yeah? If you have whatever, someone accessing bit 20 or something like that, you do that through bit shifts and masking and stuff like that. Did you do this bit magic in some lecture? Shift operation, shift left, shift right, and masking, stuff like that. Yeah, that's basically what you need to do to implement these operations. Sure. Anything else I can say here? This is testing the iterators, giving us the bits that are set, basically a positive list of the positions that are set in that implementation. Yeah, and then we have bitmap indexes. You see that in the test here. So this is a similar example to what we have on the slides here. So we have our data, and this is a list. Yeah? So we need these positions. And at some point, we're creating this index. So here we create an index type. So we loop over different index types as before. If you go up, there should be a loop here. So no, this is, let's start with the outer method. Here we go. Okay, that is the outer method. So we have different implementations of the bitmap. And each bitmap, so also equality and range encoded. You also can think about whether the type you want to index can be sorted or not, so for categorical attribute types. And then within that, nested, we have different types of bit sequences. So one is based on a list of bits, and one is based on mapping stuff to integer, as explained here on the board. Yeah, so then you have a nested loop, and then you run this method which is encoded against the interfaces and see whether these implementations fulfill the contract of the interface. That's basically what we're doing here. Yeah, I don't know. Is That's basically what I can say for today. Yeah, and we will continue with that, so I invite you to take a look at that. So far we talked about equality encoded bitmap indexes. We talked about today about these range-encoded bitmap indexes. Everything is uncompressed for the moment. We talked about different representations for these bit sequences. And we talked about how to exploit those bit lists for query processing. Yeah? That's what we had here, how to evaluate certain operations. That's a very important thing you should understand in range-encoded bitmaps, how to exploit this stuff. And we will continue with more advanced bitmap operations in January, in the first lecture in January. That's my plan, at least. With that, let's see you on Friday. Yeah?